Phoenix A, the largest confirmed black hole in the universe. 5.8 billion light-years from where you are sitting right now, there is a place where the fundamental laws of mathematics simply break down. It is a shadow so vast and so profound that our standard vocabulary for large feels like a pathetic understatement. We are talking about a physical abyss that defies the speed of light itself. Light is the fastest thing in existence, covering 186,000 miles every single second. Yet even light would take weeks of continuous travel just to cross from one side of this object's event horizon to the other. This isn't a concept from a science fiction script or a theoretical exercise in a physics lab. This is a real, physical entity. It is the single largest object ever detected by the human race. For decades, we believed we had found the ceiling of how massive these cosmic monsters could get. We had our record holders, our anchors of distant galaxies that made our own sun look like a grain of sand. But Phoenix A changed the math. It represents a cold, hard reality that the universe is capable of producing structures far more terrifying than we ever dared to calculate. When you look toward the Phoenix cluster, you aren't just looking into deep space. You are looking at the ultimate expression of entropy. It is a silent, dark titan that sits at the very edge of what is physically possible in our dimension. It is the end of the road for matter, for time, and for our traditional understanding of the cosmos. This is the absolute peak of gravitational power, a void that has spent billions of years consuming everything in its path to become the undisputed king of the dark. To truly grasp the scale of this monster, we have to look at its home, the Phoenix cluster. This is one of the most massive structures in the known universe, a sprawling, violent metropolis of galaxies held together by invisible gravitational threads. But at the dead center of this chaos lies the reason for the cluster's name and its terrifying reputation. This is Phoenix A star. For years, the astronomical community pointed to TON 618 as the undisputed heavyweight champion of the void, a black hole so massive it seemed to push the limits of reality. But Phoenix A star has effectively shattered that record. We are looking at a mass equivalent to 100 billion suns. Let that number sink in. 100 billion. If you took every single star in the Milky Way, every planet, every moon, and every speck of cosmic dust, and then multiplied that entire galaxy's mass several times over, you still wouldn't reach the weight of this one single dark point. It is the absolute apex of entropy in the observable universe. It is the most efficient engine of destruction ever mapped by human technology. Most supermassive black holes act as the anchors for their galaxies, but Phoenix A is something else entirely. It is a structural anomaly that seems to have bypassed the normal rules of cosmic growth. It doesn't just inhabit the center of a cluster, it dominates the very fabric of space-time for millions of light-years around it. This discovery is a total paradigm shift. It forces us to rewrite the chapters on how the early universe functioned and what happens when gravity is allowed to run unchecked for eons. This is the new ceiling of existence, the new nightmare, the largest confirmed black hole in the history of astronomy. When we try to wrap our human minds around the concept of size, we usually start with something familiar. We think of a mountain, a vast ocean, or perhaps the diameter of the Earth itself. If we are feeling particularly ambitious, we look toward the Sun. 1 million Earths could fit inside it, a scale that already begins to strain the limits of our imagination. But to understand Phoenix A, we have to abandon these terrestrial yardsticks entirely. They are useless here. We have to move past the planetary, past the stellar, and even past the galactic. We are entering a realm where the scale is so distorted that it feels less like geography and more like a glitch in the fabric of reality. This is the scale of the impossible, a physical presence that challenges every intuition we have about how much matter can occupy a single point in space. To visualize this, let's bring this monster home. Imagine our solar system, a vast expanse that takes our fastest probes decades to traverse. At the center sits the Sun, the anchor of everything we know. Beyond it lie the rocky inner worlds, then the asteroid belt, followed by the gas giants, Jupiter, Saturn, Uranus, and Neptune. Far beyond them is Pluto, drifting in the cold, dark suburbs of our neighborhood, nearly 4 billion miles away from the warmth of the Sun. For a human being, this distance is an unthinkable void. Yet, if you were to place Phoenix A at the center of our solar system, the Sun would be gone in a heartbeat. But it wouldn't stop there. This black hole is so gargantuan that its event horizon, the invisible border where the gravitational pull becomes so strong that nothing, not even light, can escape, would not just swallow the planets. It would extend outward, crossing the orbit of Pluto, and then keep going. It would reach a distance 100 times greater than the gap between the Sun and Pluto. We are talking about a diameter of roughly 590 billion kilometers. In this scenario, our entire solar system, with all its planets, moons, and history, would be nothing more than a tiny, insignificant speck of dust, lost deep within the obsidian belly of this titan. The sheer volume of space occupied by this object is difficult to reconcile with the fact that it is, fundamentally, a single entity. In our own galaxy, the Milky Way, we have our own supermassive black hole called Sagittarius A star. It is a formidable object, boasting a mass of about 4 million suns. For decades, it has been the terrifying center of our cosmic home, a dark sun that keeps our galaxy spinning. But when placed next to Phoenix A, Sagittarius A star looks like a grain of sand next to a skyscraper. It is a rounding error. To reach the mass of Phoenix A, you would need to take 25,000 versions of our galaxy's central black hole and crush them together. This isn't just a larger version of what we see elsewhere. It is a different category of existence entirely. It is a monolithic presence that makes the rest of the universe look fragile and thin. If you were an observer brave enough, or perhaps unfortunate enough, to approach the edge of Phoenix A, the visual experience would be unlike anything else in the cosmos. Usually, when we think of a black hole, we picture a dark sphere, a localized hole in the sky. But because Phoenix A is so unimaginably large, the geometry of its event horizon changes from the perspective of a nearby traveler. As you drew closer, the curvature of the sphere would become so slight relative to your size that it would cease to look like a ball at all. Instead, the horizon would appear to flatten out. It would look like a straight, infinite wall of absolute darkness stretching from one end of the universe to the other. There would be no top, no bottom, and no sides. Just an endless, vertical cliff of nothingness, a literal end to the world. It would be as if the universe itself had been cut in half, leaving you staring into a void that has no features, no light, and no hope of return. This infinite wall effect is a testament to the sheer radius of the object. Its surface is so vast that the curve is imperceptible, much like how the Earth feels flat to a person standing in the middle of a vast plain. Only here, the plain is made of the total absence of light. But what is even more mind-bending is the density of this giant. In the world of black holes, size and density have a strange inverse relationship. While small, stellar mass black holes are incredibly dense and exert violent tidal forces that would spaghettify an astronaut long before they reached the event horizon. A supermassive giant like Phoenix A is different. Because its mass is spread out over such a colossal volume, the tidal forces at the event horizon are surprisingly gentle. In theory, you could cross the threshold of Phoenix A without feeling a thing. You wouldn't be torn apart. You wouldn't feel the crushing weight of gravity immediately. You would simply slip from the world of light into the world of shadows. One moment, the stars of the Phoenix cluster would be visible behind you, and the next, you would be inside the largest prison in the universe. Once you cross that line, the path to the center, the singularity, becomes inevitable. Because the distance from the horizon to the center is so vast, you might actually live for weeks or even months inside the black hole before reaching the end. You would be a ghost haunting a dark kingdom, a traveler in a space where time and space have swapped roles, drifting toward a core that contains the mass of 100 billion stars. This mass, 100 billion suns, is the true heart of the mystery. To put that in perspective, the Milky Way galaxy is estimated to contain between 100 and 400 billion stars. This means that Phoenix A, a single object, weighs as much as a significant fraction of our entire galaxy. It is a concentrated point of gravity, so powerful that it doesn't just influence the stars near it, it dictates the evolution of the entire Phoenix cluster. This cluster is a collection of thousands of galaxies, all swimming in a sea of superheated gas that glows with the intensity of millions of X-rays. In most clusters, this gas eventually cools down and falls into the galaxies to form new stars. But Phoenix A is so active, so hungry, and so powerful that it pumps staggering amounts of energy back into its surroundings. It acts like a cosmic thermostat, its massive jets of energy preventing the gas from cooling, effectively halting the birth of stars in its vicinity. It is a king that demands total stillness in its court. When we look at the light coming from the Phoenix cluster, we are seeing a snapshot from 5.8 billion years ago. At that time, our own Earth didn't even exist. The sun hadn't yet ignited from its primordial cloud of gas. While the first sparks of life were still billions of years away on our world, Phoenix A was already sitting there, a finished masterpiece of gravitational collapse, having already consumed more matter than we can ever hope to map. It represents the absolute peak of entropy. In the grand timeline of the universe, stars will eventually burn out, galaxies will drift apart, and the light will fade. But black holes like Phoenix A will remain, growing larger and colder, outlasting everything else. They are the final chapters of the cosmic story. The existence of Phoenix A challenges the very models we use to describe the growth of the universe. We used to think there was a natural limit to how big a black hole could get, a heat limit, where the radiation from the matter being swallowed would push away any further food, starving the giant. But Phoenix A has bypassed those limits. It has grown into a stupendously large black hole, a titan that defies the standard life cycle of cosmic objects. It stands as a silent reminder that the universe is far more extreme than our early theories suggested. It is a place where the numbers stop making sense and where the scale of the impossible becomes a terrifying physical reality. We are not just looking at a large object. We are looking at the ultimate destination of matter. 100 billion suns crushed into a single dark point, hidden behind a horizon so wide it could swallow our entire corner of the galaxy without leaving a trace. This is Phoenix A, the undisputed heavyweight champion of the dark, a monument to the sheer, overwhelming power of gravity in its most absolute form. The existence of such a gargantuan entity as Phoenix A brings us to a profound scientific crossroads, a point where our current understanding of the universe begins to fray at the edges. When astrophysicists look at a monster of this magnitude, the first question isn't just how big it is, but rather how it is even possible for something like this to exist in the first place. According to the standard model of cosmic evolution, black holes grow by two primary methods. They either consume surrounding gas and dust, or they merge with other black holes during galactic collisions. However, there is a fundamental speed limit to this growth, known as the Eddington limit. As a black hole feasts on matter, the material swirling around it heats up to millions of degrees, creating an intense outward pressure of radiation. If the black hole tries to eat too much too fast, this radiation pressure becomes so powerful that it literally blows the food away, effectively starving the black hole and slowing its growth. When you apply this math to the 13.8 billion years the universe has been in existence, the numbers for Phoenix A simply don't add up. There hasn't been enough time since the Big Bang for a standard black hole to grow to 100 billion solar masses by eating alone. This realization has forced the scientific community to propose a new, terrifying category of celestial objects, the SLABs, or stupendously large black holes. The term stupendously large might sound like hyperbole, or perhaps a lack of creative naming, but in the world of high-level physics, it represents a very specific and radical departure from the norm. Most of the supermassive black holes we know, like the one at the center of our own galaxy, are thought to have started as seeds, the remnants of the very first generation of massive stars that collapsed shortly after the dawn of time. These seeds were small, maybe 100 times the mass of our Sun, and they spent billions of years slowly accumulating bulk. But Phoenix A is so far beyond that scale that the seed theory begins to fall apart. To reach this size, Phoenix A couldn't have started as a star. It must have been born big. This leads us to the theory of direct collapse. In the chaotic, high-density environment of the very early universe, it is possible that massive clouds of primordial gas didn't bother forming stars at all. Instead of fragmenting into small pockets to ignite nuclear fusion, these clouds, millions of times the mass of the Sun, might have simply succumbed to their own gravity all at once. They would have skipped the entire stellar life cycle, collapsing directly into massive seed black holes that were already the size of entire star clusters the moment they were born. Even with a head start like that, the journey to 100 billion solar masses requires a history of unimaginable violence. The Phoenix cluster, where this titan resides, is one of the most active and crowded regions of space ever observed. It is a cosmic intersection where hundreds, perhaps thousands of galaxies have been drawn together by gravity over eons. The life story of Phoenix A is likely written in the blood of these galaxies. We have to envision a multi-billion-year sequence of galactic cannibalism, where Phoenix A sat at the center of a gravitational whirlpool, watching as entire galaxies were pulled into its orbit. As these galaxies collided, their own central black holes, already massive in their own right, would have eventually spiraled inward, dancing a lethal orbital ballet before crashing into Phoenix A. Each of these mergers would have sent ripples through the very fabric of space-time, gravitational waves so powerful they would have vibrated through the entire observable universe. Phoenix A isn't just a single object, it is a graveyard, a collective accumulation of the mass and energy of thousands of dead worlds and fallen stars, all compressed into a single, unescapable point of no return. The sheer activity of the Phoenix cluster provides another clue to the nature of this beast. Most ancient, massive galaxy clusters are red and dead, meaning they have long since stopped producing new stars because the gas within them has become too hot to collapse. But the Phoenix cluster is different. It is experiencing a starburst of incredible proportions, creating hundreds of new suns every year. This suggests that the relationship between Phoenix A and its environment is a complex, high-stakes feedback loop. The black hole is so massive and its gravitational influence so far-reaching that it acts as a central engine, pumping out jets of high-energy particles that blast through the surrounding gas. These jets create enormous cavities in the intergalactic medium, bubbles of plasma that are millions of light-years across. It is a delicate, albeit violent, balance. The black hole feeds, it screams out energy in response, and that energy reshapes the entire cluster, dictating where stars can be born and where the gas must remain thin. Phoenix A is not just a passive observer of its cluster. It is the master of the house, the ultimate architect of its own cosmic neighborhood. But even a titan like this is subject to the slow, relentless march of time and the laws of thermodynamics. When we think about the future of Phoenix A, we are forced to think on scales that make the current age of the universe look like a mere blink of an eye. Eventually, the feeding will stop. The gas in the Phoenix cluster will be exhausted. The nearby galaxies will have all been consumed or pushed away, and the universe will continue its accelerating expansion, leaving Phoenix A isolated in a cold, dark corner of the void. At this point, the black hole will begin the longest, slowest death imaginable through a process known as Hawking radiation. Quantum effects at the edge of the event horizon will cause the black hole to very slowly lose mass, emitting a faint glow of particles over unimaginable spans of time. For a black hole with the mass of 100 billion suns, this process is so slow it defies description. We are talking about a time frame of roughly 10 to the power of 100 years, a number so large that if you tried to write it out with every zero representing a single atom in the universe, you would run out of atoms long before you finished the number. During this incomprehensible epoch, Phoenix A will likely be one of the last remaining structures in existence. Long after the last star has flickered out, long after the last white dwarf has cooled into a black cinder, and long after the galaxies themselves have dissolved into stray atoms, Phoenix A will still be there, a silent, dark monument in an empty universe. It will be a sovereign of a kingdom of nothingness, holding onto its stolen mass until the very end of time. When it finally does evaporate in a final, microscopic flash of energy, the universe will truly be empty. It is the ultimate expression of the heat death of the universe, the point where entropy finally wins, and the last concentrated pocket of energy is surrendered back to the void. Reflecting on Phoenix A is a humbling exercise in human insignificance. We live our lives on a small, rocky planet, orbiting a perfectly average star in a quiet suburb of a standard spiral galaxy. We measure our history in centuries and our distance in miles. But Phoenix A stands as a reminder that the universe does not operate on a human scale. It is a place of extremes that we are only just beginning to map. To look at Phoenix A is to look at the limit of what nature allows to exist. It is a physical manifestation of the word absolute. It is the most massive, the most powerful, and the most enduring thing we have ever found. It challenges our math, it breaks our models, and it forces us to reconsider the very origins of our cosmos. It is the king of the abyss, a shadow that spans the stars, 100 billion suns lost in a single point of darkness. In the grand tapestry of the heavens, Phoenix A is the final heavy period at the end of the cosmic sentence, a silent titan that will outlast everything we have ever known and everything we will ever be. It is the largest confirmed black hole in the universe, and it is a window into a scale of reality that is as terrifying as it is beautiful. This is the end of the line. This is the peak of gravity. This is Phoenix A.